Hey friends, my name is Bill Payne. I'm a former geologist turned science teacher. I wanted to talk about defending claims based upon evidence, critically evaluating unifying concepts in light of empirical data. I wouldn't have seen it if I hadn't believed it. There's a lot of truth in that. We tend to believe things first and then we see what it is that we're looking for as we make observations of the world around us. As we look at this earth that we call home and we try to reconstruct the past history of earth, we're strongly influenced by what we believe as to how we interpret the data to reconstruct the history. Charles Darwin said a fair result can be obtained only by fully balancing the facts and arguments on both sides of each question. And Richard Feynman, I would rather have questions that can't be answered than answers which can't be questioned. Here we see a mountain in British Columbia, Canada, and there is sedimentary rock at the top of the mountain. You can see these layers. This was probably laid down on the bottom of a shallow inland sea and buried compaction turned the sediment into rock. Then it was uplifted. And today we see erosion, slow and gradual erosion by glacial ice and hot and cold cycles eroding the rock and bringing it down into the valley. So this illustrates the most fundamental principle in geology, uniformitarianism, which says the present is the key to the past. So today we see this mountain being slowly eroded, so we can infer that in the past it did the same thing. It was eroding very slowly over time. So what assumption is being made here? We're actually assuming that the past was just like the present, but that's a question that is not necessarily true. Let's begin by looking at where the Titanic sank. Let's consider what's required for the preservation of bones and articulated skeletons in the fossil record. Here's the Titanic ship, where it came to rest on the bottom of the North Atlantic. The Titanic is now at 12,600 feet below the surface of the ocean. And notice at that depth, even though it's cold and dark, there's plenty of animals that live down there and looking for food. Here we see in the debris field, which is about 105 years after the Titanic sank, we see a sea spider here, and we see a pair of shoes. But what we don't see is the person that was wearing those shoes when they sank to the bottom. Here we see a shoe here, or a boot, and what appears to be clothing, but there's no evidence whatsoever of a human body still surviving there. So if these human skeletons are gone after only 105 years, how is it that bones and skeletons are preserved in the fossil record? When fish die, we see that they bloat, then they float, they decay, sink to the bottom, and their skeletons disarticulate. There was an experiment on a crocodile that was placed in an aquarium in a lab, and the fresh crocodile was in the water. Then by day 2, it was beginning to bloat and float, and then it was subjected to decay. By day 44, almost all of the flesh had decayed, and then it had sunk and disarticulated. So it says, while floating, skeletal elements remained articulated. Majority of disarticulation occurred at the sediment-water interface after the carcass sank during the advanced decay stage, about 36 days post-mortem. Based on these results, we conclude that the fossil crocodile specimens displaying high levels of articulation are not the result of prolonged subaerial and subaqueous decay in a low energy aqueous environment. Dead whales float and are subject to scavenging, probably by sharks, and decay by bacterial action. Eventually, they may sink to the bottom of the ocean, but we saw at the Titanic 105 years after laying on the bottom, they would be completely disintegrated. So let's look in the desert in Egypt. Whale skeletons are part of the fossil record, though. Here we see one in the desert of Egypt. It seems that the skeleton is very well preserved. And here we see another one in the same Egyptian desert. The bones are all lined up and the ribs are intact and in place where they should be. Let's go from Egypt over to South America. We see here in the Chile desert 3 whales that are buried together, the 2 adults and a baby whale. The chances of these 3 whales dying a natural death and being buried together are nil. There must have been a catastrophe, a watery catastrophe that washed them into this common grave and quickly buried them with sediment in order for this preservation to have occurred. Here's a fish from the mountains of the Himalayas. Notice the very good detail for the fins and the bones. And there were no bones here, but this is flesh that was actually preserved. So this suggests that this fish was buried very rapidly. It did not float around and decay and eventually sink. It was buried catastrophically. Here's a fish that died while eating another fish. Here we see a well-preserved tetrapod. And this is a pregnant female plesiosaur that was buried along with her baby. In this picture, there's probably 6 or 7 dinosaurs buried together. And apparently these were buried in a catastrophic flood environment so that all the carcasses were washed in together and rapidly buried before the bones had time to deteriorate. So if an animal dies on land, what happens to it? Does it become a fossil? No, it's eaten by scavengers, and then the bones are torn apart. It's disarticulated. Dinosaurs are found all over the world. In fact, on every continent, even Antarctica, we find dinosaurs. So this was not an unusual thing. It's not just a little local catastrophic burial, but we see this as worldwide. Something was going on all across the world to create the death and preservation of these animals. Okay, let's go down to the tip of South America and Argentina. There we find the Santa Cruz River is in a big valley, but by comparison, the river is very small. Charles Darwin read Charles Lyell's book, Principles of Geology, and it promoted uniformitarianism, which strongly influenced the thinking of Charles Darwin. He sailed around the world in the 1830s, reading Lyell's book and adopting uniformitarian presuppositions. In 1834, Darwin went up the Santa Cruz River thinking about the erosion of the river in uniformitarian terms. So here's what he saw, the Santa Cruz River meandering up through this valley. The river itself is only about 1/10 of a mile wide, whereas the valley is about 10 kilometers wide. Darwin considered this, and he said in his diary, he wrote, "The river, though it has so little power in transporting even inconceivable fragments, yet in the lapse of ages might produce by gradual erosion an effect of which it is difficult to judge the amount." Darwin missed some important observations, though. These rounded boulders were rounded off by flowing water, and they can be found down in the river valley, on sandbars in the river, and up on top of this basalt plateau above the river. I don't think Darwin continued all the way up to this lake and to the Andes Mountains to the west, but if he had, he would have seen, or he might have seen glacial ice such as this, And this would be another hint that might help to explain what we see as the erosion in the Santa Cruz River Valley. Let's go from here up to Washington State. We're going to look at the scablands in eastern Washington State. So the scablands are located here, and then we're also going to look over in Montana. Did this 200-foot tall waterfall cut this huge canyon? Here's some more erosion in a different area. This is called dry falls. There's no water at all coming over here, just a pond of water down here at the bottom of these falls. But what caused this erosion? Here we see the same thing again. The dry falls are over there. No erosion, no agent of erosion is evident in this view. Looking down on this dry falls area, we see the erosion all the way around here. This white circle is salt that was precipitated out as water evaporated out of that pond. You can also see linear features of erosion in this extrusive igneous basalt that forms on the cliff tops on either side of these eroded areas. So over in this view, we see a little bit of a stream coming down over here, but it's not reasonable to assume that this little stream did all of this erosion. Now we begin to see a large lake upstream of this area where it's been eroded, and so we begin to think that this was floodwaters that came through this area, and these cliffs are about 385 feet high, and the water must have been about 265 feet above the top of these cliffs. And the reason we say that is because we can see where this topsoil has been scraped away or washed away down to the bare basalt surface on this side and across over here. And so that's where we get the height of the floodwaters that must have stripped the topsoil off of the bare rock and also done this erosion. Harlan Bretz was a geologist who did extensive field work describing these channeled scablands. He published a paper in 1923, said the channel scablands were caused by massive flooding in the distant past. This was seen as arguing for a catastrophic explanation of the geology against the prevailing view of uniformitarianism. For that reason, his views were immediately discredited. He encountered resistance to his theories, partly because his theory implied the possibility of a biblical flood, which the scientific community strongly rejected. He also didn't know of a source for the massive floodwaters his theory required. Looking in Montana to the east of the scablands, there's another geologist, Joseph Pardee, found evidence of an ancient lake in Montana, created by an ice dam 37 kilometers wide, 0.8 kilometers high. He discovered that when the ice dam broke, it released water that flowed west toward the scablands. Now Bretz had a source for the massive flood that he said carved the scablands. Here we can see wave-cut terraces across the side of this mountain. In this view, you can see the shorelines across here and over here. And the town, this is Missoula, Montana. This town was once under 945 feet of water. So here's where the ice dam was. Here's the town of Missoula that was under almost 1,000 feet of water. And this is an illustration of how an ice dam might work. This dam would be draining or blocking the drainage from this water that's backed up here. So here's the ice dam, the glacial lake. Missoula is behind the dam. And eventually the dam broke, though, and when it did, it released all of this water, and it flowed across this area here on its way out to the Pacific Ocean. So here's the path that the floodwaters took as they eroded the scablands. So now we can see that this 60-foot or 60-meter waterfall did not cut this canyon, or this over here, and this stream right here did not cut this canyon either. This erosion was done by a catastrophic flood released as a result of a glacial outburst of water that was backed up behind the dam, the glacial dam. We also see ripple marks in this area in the scablands. These are nearly 50 feet high and up to 490 feet apart. Huge ripple marks formed as water flowed through this area. This is the barn for comparison, for scale. So Bretz spent 40 years arguing his case for a catastrophic origin for the scablands. As more data came available, the arguments of Bretz and Pardee eventually won the day. In 1979, 56 years after publishing his first paper, the Geological Society of America awarded Bretz the Penrose Medal, the field's highest honor. Bretz was 96 years old. He joked to his son, "All my enemies are dead, so I have no one to gloat over." Philosopher Thomas Kuhn observed, "New scientific truths often win the day, not so much because opponents change their minds, but because they die off." So Charles Darwin, at the Santa Cruz River in South America, he assumed slow and gradual erosion by the Santa Cruz River cut the 10-kilometer wide valley. Darwin failed to consider the mechanism required to round and transport the rounded boulders and gravel 90 meters above the river. The Santa Cruz observations can be explained as a result of a glacial outburst similar to what we see for the scablands in Washington state. So we've looked at two locally catastrophic glacial outbursts that eroded the Santa Cruz River Valley and the scablands of Washington state. These catastrophic events were initially interpreted within a uniformitarian framework, which was eventually shown to be incorrect. So let me ask the question, are there other geological processes that have been incorrectly interpreted due to a uniformitarian mindset? Let's look at the deposition of clay and silt. These are very fine-grained particles, so it takes long periods of time for clay and silt to settle out of water, out of suspension. And about 80% of all the sedimentary rocks in the geologic record are fine-grained mudstone or shale. The conventional idea for the formation of fine-grained mudstones, slow and gradual sedimentation in quiescent waters over a long period of time. So here's a picture of a shale outcrop, the silt and clay particles that make up this shale, and it's assumed to take a very long period of time to deposit this material. There's an experiment that was done using flume experiments. We investigated the bedload transport and deposition of clay floccules. Floccules are clay particles that clump together to form these floccules, and we find that this occurs at flow velocities that transport and deposit sand. So maybe it doesn't take so long if the water is not still quiescent but instead flowing, then now we see that the clays can form floccules and be deposited along with sand. Here's a scanning electron microscope image of kaolinite clay. You can see some of these particles of clay are less than 1 micron in diameter. In flowing water, these clay particles clump together in floccules. The floccule illustrated here measures 0.12 millimeters in this long direction, meaning it's large enough to settle out with sand particles. So this is flowing, not quiescent waters required to produce these beds that are found in many mudstones. So taking an actual shale and cutting it in cross-section, you can see the diamond saw blade cuts across here, but these are the beds of the sand and silt and clay. And you can see that these are cross-bedded or cross-laminated shale. So these beds were deposited in flowing water, not quiescent and still water. So the conclusion, many ancient shale units, once examined carefully, may reveal that they accumulated in the manner illustrated here, rather than having largely settled from slow-moving or still suspensions. This, in turn, will likely necessitate the re-evaluation of the sedimentary history of large portions of the geologic record. So the uniformitarian view was it's slow and gradual erosion deposition over long periods of time. This experiment here and the Flume experiment says no, that's perhaps incorrect. Okay, let's go to Yellowstone. There's 27 ancient forests said to be stacked one on top of the other one. Here's an ancient fossilized tree trunk, and here's another one down below it, and one off to the left, I think. And in the background, you can see the modern forest today. So what would be a more natural interpretation than to say the natural forest is growing here today, and in the ancient past we had these large trees that grew, and here they are preserved in growth position. This sign from Yellowstone National Park illustrates for us what these trees might have looked like. We have the 27 horizontal layers and stacked one on top of the other, and these ancient trees are buried within those layers. A close look at the trees at Specimen Ridge reveals some interesting things. We find that there is no topsoil horizon associated with the trees. We find diverse plant species together that don't grow together today. Needles and broadleaves are sorted where normally they would be mixed. The tree ring sequence is the same for trees buried at different levels, proving they grew at the same time, but they weren't buried at the same level. The horizontal logs are aligned with the long cross-section axis of non-circular vertical stumps, suggesting deposition in flowing water. These things all tend to be lined up in a preferred direction associated with the flow direction of the water. The feldspar grains are not weathered to clay. The tops of overlapping vertical trees are not decayed. There's a general absence of bark on these trees, similar to what we see at Mount St. Helens. And there's the absence of any animals except for the remains of termites in wood chambers. When Mount St. Helens exploded, the horizontal force of the blast knocked down mature trees, knocked them over, and then debris, landslide material from the volcano slid down into the lake, creating a water wave that washed up on the mountains around the lake, and the water picked up the trees that had just been knocked down by the steam blast and washed them back down into the lake, where a lot of them are still floating today. Notice that these trees don't have any bark on them. The bark has been rubbed off the trees, gotten waterlogged, and sank to the bottom of the lake. A lot of these trees also got waterlogged, and as the root end soaked up water, it became heavier than the rest of the tree, causing the root end to sink first. And so you see a number of trees floating vertically in the water. These that are leaning over have lightly grounded, and there's maybe one or two in the background that are touching the lake bottom, so they're tilted over. But these that are vertically upright are freely floating in the lake. We see that as these trees sink, they hit the bottom, and then organic material continues to pile up around the trees. And so these trees did not grow here, but they are buried in growth position. And they overlap in as far as the horizon where they originate. The roots of this tree are down deeper than the roots of this tree and the roots of this tree. And so these trees could have grown at the same time, but they got buried at different levels. So the tree rings of this tree may be identical to the tree rings of this tree, showing the fact that they grew at the same time, even though they're buried at different levels. The volcano ripped up tree stumps that had been previously logged, so these tops of these trees had been cut, and then the volcanic activity ripped these stumps out of the ground, and a lot of them still have roots or short roots attached to them. and it washed them down the Toutle River, and then they were deposited in an upright position. So here we see upright stumps, and this is a good analogy for what we see at Specimen Ridge. From here, let's go down to the Grand Canyon and think about the erosion of the canyon. This is the Kaibab Arch. This is about 3,000 feet higher elevation than the plateaus on either side of the arch. So if the Grand Canyon did not cut through that arch, there would be water impounded back up here behind the upwork or the arch, and it could have backed up water in these lakes, similar to what we saw at Missoula in Montana. And then if the arch was breached, this water could have been drained out catastrophically and eroded this canyon in a short period of time. Here's the Grand Canyon that we see today in the Colorado River. Did this river do all of this erosion over a long period of time, or was it catastrophic in a short period of time? Looking back at Mount St. Helens, there was landslide material that came off the mountain and slid down and blocked the drainage from Spirit Lake and slid off into the North Fork of the Toutle River. And then a couple of years later, there was a mud flow that came down the mountain, and it eroded this canyon. This is over 100 feet deep. It eroded this canyon into that debris material, the landslide material that had been deposited by the explosion from Mount St. Helens. So this looks very much like the canyon at Grand Canyon. You've got the main canyon, and there's a small stream that flows down through here. And you've got these side canyons also, as we see at Grand Canyon. So here's a closer view of that same canyon, over 100 feet deep, and a very small stream flowing down through here. This stream did not erode the canyon. The canyon has captured the stream, but the canyon was here as a result of catastrophic erosion, and now today we see the stream flowing down through here. Let's talk about paraconformities and the missing time that's supposedly represented by the break between one layer and the next. A paraconformity is a flat gap between two rock formations. If in the distance there was a third formation deposited between the upper and lower formations, and if we estimated a time of 6 million years to deposit this formation in the middle, and then it pinches out and doesn't show up over here, we would still have to assume that there's a 6 million year gap between the lower formation and the one on top. During that 6 million years, there should have been some erosion that occurred to erode this bottom formation before the overlayer, the top formation, was deposited. Here we see two paraconformities, one with 10 million years of missing time, another one with 20 million years of missing time, yet there's no erosion below the paraconformities. This paraconformity supposedly represents 6 million years of missing time. We have the Coconino sandstone above the paraconformity and the Hermit Shale below. Shale is a fairly soft rock. It's easily weathered or eroded. The Hermit Shale fossils consist of ferns, conifers, and other plants, and some fossilized tracks of reptiles and amphibians. So this was subaerial, supposedly for 6 million years, and yet we see nothing but a fresh contact at the top of the Hermit Shale. So here's the Coconino and the Hermit Shale, 6 million year gap, just stretches as far as the eye can see. 14 million year gap. Here's 100 million years and no erosion. Missing time, no erosion. Let's look at the nautiloid bed that's found in Grand Canyon. A nautiloid is an extinct marine creature resembling a squid, which had a solid chambered shell. Here's the fossil nautiloid, and these things can be several feet long. These fossil nautiloids occur right along the middle of this 7-foot thick Redwall limestone bed. So why are they only in the middle of this formation? I think the answer is there was a debris flow or turbidity flow. This is all underwater, and this flow hydroplaned across the ocean bottom, and this bottom half of the flow was high density, so the nautiloid shells were swept up, carried along with the flow, came back over here and settled on top of this high density layer. About 15% of these shells are preserved in a vertical orientation. So how far does this nautiloid bed extend? It goes from the head of the Grand Canyon all the way over to Las Vegas, a total of about 175 miles. So how do we interpret what we see? This is a canyon length area. It was caused by an ocean floor collapse event. A gigantic sandy debris flow was created, killed the nautiloids, swept them up, buried them in lime sediment, and then the back surge deposited silt above the nautiloid fossils, and the limestone strata then was deposited in minutes. Let's talk about the formation of coal beds. Coal deposits are said to have formed in vast swamps as vegetation collected over thousands of years. So let's look at the conditions required for vegetation to collect in thick mats in a swamp, features we would expect to see in coal from a swamp deposit versus features we actually see. Here's an illustration of what these ancient coal swamps supposedly look like. You've got trees that grew and they died, they fell over, and so the organic matter collected on the bottom of the swamp and piled up to form these peat mats that supposedly eventually became coal. And so Hobart King on geology.com makes a statement: for a coal seam to form, perfect conditions of plant debris accumulation and perfect conditions of subsidence must occur on a landscape that maintains this perfect balance for a very long time. Slow and gradual, uniformitarian process. So here's another swamp, and vegetation will die and pile up, but if it gets too high, then the vegetation decays. So we have to have the land sink as the vegetation piles up. If the land sinks too fast, the trees drown, and so we don't have a coal deposit or vegetation deposit there either. It's got to be in perfect balance. We see the uniformitarian explanation requiring millions of years of slow and gradual deposition in ancient swamps. So here's the ancient swamp that's hypothesized, and here's the coal seam that we see today. If a flood of water washed a layer of sediment into the swamp, or if a layer of volcanic ash covered the swamp, the standing trees would block the continuity of the layer. What do we actually see in coal seams? Well, these are called partings. This is coal, and then these inorganic layers are interfingered with the coal. And so if this was a swamp, there should have been trees standing around here, and this would have been preserved along with the partings. But we don't see that. We see the partings that seem to just flow unrestricted over a wide area. Here's a picture of a piece of coal. You can see this banded horizontal layer. This is primarily tree bark, these shiny layers. And then here's a inorganic layer right here, a minor parting. Here's a larger parting, coal above and below the parting. We see razor sharp contacts. We don't see any roots from this coal seam up here. If this was a swamp, there should be roots coming down. And if this was a swamp down here, there should have been trees, stems of trees going up into this parting. Don't see that. Let's take a detailed look at the Heron coal in Illinois. This Heron coal is actually that line right there, and it's occurs in this area right here, about 400 kilometers north-south. And it's got partings in it, though, that can be traced. The upper clay parting averages 3 millimeters thick, not very thick. The blue band in the middle averages 2.5 to 7.6 centimeters thick. And then the lower parting is about 1.3 centimeters thick. Well, how far did these partings spread? These three partings are traceable through a belt ranging from 900 kilometers northwest to southeast, from north-central Iowa to western Kentucky, 700 kilometers southwest to northeast. And that's a problem. If this was a swamp, how would you get these very thin partings to extend over this large distance? The author of this paper, Mr. H.R. Wanless, said a principal problem to explain in any case is how the forest vegetation of a swamp could be so completely leveled as to permit accumulation of a continuous layer of clay averaging an inch or so in thickness. This is in Australia. Here we see parting of volcanic ash, and it's very flat, level. So how can you completely level this swamp so that you can get these partings? Wanless realized what the answer must be to this principal problem. He said if one argued for an allothenous or transported origin for the coal, the vast known extent of these and other coal beds would make such an interpretation impossible, for there would be no available source for the vegetation whose detritus was to cover such vast areas. Wanless saw thin partings in coal that covered some 400,000 square kilometers, realized this required a broad, flat depositional area such as the seafloor, but he could not imagine a source big enough for floating organic debris to make coal seams. So we have peat, which is what forms in swamps or marshes, and it doesn't have that horizontal structure, though, that we see in coal seams. The authors of this paper proposed that this swamp could be a modern analog for the formation of coal seams. But the problem is this material is intensely root penetrated, and you've also got this watercourse that cuts through the swamp, and so there's nothing horizontal about a swamp except maybe the surface of the water. But there's no way you can start with this swamp material and end up with a banded coal. So geologist Steve Austin did his research on a coal seam in Kentucky. He showed the coal seam could not have come from a swamp, but he had to provide an alternate explanation. He adopted the floating mat model for the formation of the coal seam. He defended his dissertation in 1979, and this is an illustration of this floating mat that rains peat down on the floor of this transgressing sea. 10 months after defending his dissertation, on May the 18th, 1980, Mount St. Helens exploded, providing a lab for Austin to test his floating mat model. So here we see the log mat at Mount St. Helens on Spirit Lake. We notice that these trees don't have any bark on them. The bark got rubbed off as the logs rubbed against each other. The bark was waterlogged and sank to the bottom of the lake. Here we see a piece of tree bark laying on the bottom, and this bark is now stacked up about a meter thick on the bottom of Spirit Lake. So this bark forms these horizontal layers that would match what we see in coal seams. There's no roots in the coal, no tree trunks in the coal. It's just bark, bark, bark stacked up. So that checks out. Features of typical coal seams: planar, widespread partings, sharp top and bottom contacts with adjacent clastic material, general lack of roots below the coal, general lack of vertical trees above the coal, and they may drape over irregular topography. Here's a strip pit, and I walked up and down the length of that looking at 1, 2, 3, 4, 5 coal seams, and there's one tree in all of that strip pit. Did that tree grow there, or was it rafted in? Did it float in? If we look in Pennsylvania at the Pittsburgh coal, It's about 2 meters thick, and in places it contains a parting as well, which is extensive. And here's drill hole data for this ribbon diagram. You can see these partings, and this is Pennsylvania, Ohio, West Virginia, Kentucky. So this is a large area that this one coal seam covers, and you can see these partings that do extend over a large area. Coal seams are not rare; they're all over the world, and so there's got to be some explanation that unifies all of these separate deposits. Let's consider the rate at which mountains are being eroded. We can look at Mount Everest, the tallest mountain in the world. And as we see the mountain, we notice these layers, sedimentary rock up here at the top of Mount Everest. Notice also the glacial ice that's eroding the mountain down and pulling fragments of rock down into the valley. But the mountains are being eroded by glaciers, and this glaciers, so they come down the valley, they drop their sediment down through here, and we can see that at the top of Mount Everest, there is limestone, Ordovician age limestone, which is marine. It contains marine fossils. So this Ordovician limestone is being eroded today, and so there must have been other material above it in the past that eroded down to expose the limestone that we see up there on top of the mountain today. So erosion rates of 1,000 millimeters per 1,000 years, or 1 millimeter per year, are common. The Himalayas are said to be 50 to 60 million years old. In 50 million years, how much erosion would have occurred? Assuming the present measured rate of erosion, 1 meter in 1,000 years, and assuming a uniformitarian rate, in 50 million years, 1 meter per 1,000 years would give us 50,000 meters of erosion, or 50 kilometers that have been eroded. If we assume 50 kilometers of sediment above the Ordovician, that's twice as much sediment as is found in the deepest sedimentary basin in the world. The Caspian Basin has 15 to 25 kilometers of sediment. So here's the Caspian Basin up here, the deepest basin in the world, no more than 25 kilometers of sediment. Nevertheless, let's assume at one time there was 50 kilometers of sediment above the Ordovician. And if you go down, this is kilometers, if you go down 50 kilometers, you're going to get burial temperatures up to about 500 degrees. And if you're at 500 degrees, and if you come down, this is only 30 kilometers, but if you go down that deep, you're already in high-grade metamorphism. If you went down 50 kilometers, the rock would melt, it would become igneous. So here we see the summit limestone containing fossils at the top of Mount Everest. The limestone could not have been buried 30 kilometers. If it had been, it would have been metamorphosed to marble and the fossils destroyed. So how old could Mount Everest be? Here we see the fact that the sedimentary rock, the limestone, has not been metamorphosed, so it could not have possibly been deeper than about 7 kilometers depth of burial, maximum depth of burial. If it has been eroding at the rate of 1 meter per 1,000 years, multiply that by 7,000 meters, and we get a maximum age for the summit limestone, Mount Everest, of 7 million years. Could have been less than that, but it could not have been more than 7 million years old. We see two major problems with the supposed 50 million year age of Mount Everest. First, there's no basin in the world deep enough to hold 50 kilometers of sediment. Second, the summit limestone is not metamorphosed, which it surely would have been if buried that deeply. Based upon the empirical data and making uniformitarian assumptions, we're forced to conclude that the conventional age of 50 to 60 million years for Mount Everest and the Himalayan mountains is exaggerated by at least 7 orders of magnitude, and it could be much more than that. So in recap, We looked at the conditions required to preserve dinosaur fossils. We saw that it had to be rapid burial by sediment-laden water, and we noticed that we have dinosaur fossils found on every continent. So this raises the question, were these individual floods that buried all these dinosaurs, or was this one global catastrophe that buried everything at one time? We also looked at the Santa Cruz River Valley. Notice that the river flows very slowly, but yet it is, Darwin thought it had eroded this 6-mile wide valley, and he failed to notice the round boulders that are rounded by flowing water, which this river, of course, doesn't have the energy to transport those boulders and round them off. We looked at the dry falls in the Scablands. We see a little bit of water there, but nothing like the flood waters that were required to create this erosion. We looked at how clay particles can flocculate in flowing water, and therefore they do not require quiescent conditions over long periods of time, but can be deposited rapidly. We looked at Grand Canyon and we asked the question, could this have been a catastrophic erosion event to create all of this erosion, similar to what we saw happen catastrophically at Mount St. Helens? We looked at Grand Canyon. We saw the paraconformities that don't have any erosion at that contact between the formations. These formations, the paraconformities, represent missing time up to 100 million years and no erosion between the layers. We looked at the nautiloid fossil deposit in Grand Canyon in the Red Wall limestone, and we saw that this was a catastrophic deposit laid down probably in a matter of minutes, if not hours, but certainly not over thousands or millions of years. That raises the question for us, could there be other deposits in Grand Canyon that were also deposited catastrophically? We looked at the formation of coal, and we showed that the swamp model does not result in the features that we see in coal. In order to get these features, the best model that we have come up with so far is the floating mat model developed by Steve Austin. The floating mat model, of course, requires water to cause the organic mat to float. And we see coal seams all over the world. And so I guess the question is, was this one global catastrophe to cause all of these mats of floating organic material to deposit and turn into coal, or was it a series of individual floods? We looked at the fossiliferous limestone on Mount Everest, and we noticed it has not been metamorphosed into marble, which calls into question the conventional estimated age of the Himalayan mountains of 50 to 60 million years, and causes us to ask the question, could there be other ages in the geologic timescale that might be incorrect? We looked at a broad range of empirical data which should be included in the science curriculum to allow students to critically evaluate various unifying theories in Earth history. Darwin said again, fair result can be obtained only by fully balancing the facts and arguments on both sides of each question. And Feynman, I would rather have questions that can't be answered than answers which can't be questioned. So we start out with what we believe, and then we look at the empirical data, which is filtered through what we believe, and we come out basically with either a uniformitarian viewpoint or a catastrophic viewpoint. It could be a combination of those, but there are, as we have looked at, there's a lot of uniformitarian assumptions that don't really match the data. There's lots more I could have covered, but just ran out of time. But if you need more information, feel free to email me.